All right, so let's recall just a few basic ideas. Actually, first of all, the central question. If we have a sequence Fn goes to F pointwise, how continuous is F?
It's continuous on a dense subset.
Yes, so you're already stopping the fun there, right? But, but we know that if Fn is uniformly convergent to F, then F is very continuous. It's going to be continuous everywhere, right? Now, the question in this case is what happens if it's just a pointwise limit? We know that discontinuities can occur. So, for example, if you consider x to the n, the sequence of polynomials x to the n over the interval from 0 to 1, this function will have how many discontinuities in the limit? So, x to just the power functions. X to the n, if I take n to infinity, I get a function that has how many discontinuities? Just one. Where? At x equal to 1. The function that x to the n converges to is 0 everywhere except at 1, where it's equal to 1. Right? So let's recall a few facts. So first thing we learned is that if we have a sequence of dense open sets, in R or in a complete space, the intersection is, what is this? So if I intersect a bunch of dense sets that are open, the intersection will be, do you remember? Dense, in fact, uncountable and dense. But we need dense here. That's Baire category theorem. And it's useful in describing discontinuities, if you remember. It's because you realize that the set of discontinuities is an F sigma set. It can be written as a union of closed sets. It's a countable union of closed sets. So then we have this business of first and second category. So we say that a set V is a first category set if V can be written as what?
Union of no identities.
Very right, correct. As a countable union. So, in other words, V is equal to the union of En, where the interior of the closure of En is the empty set. So nowhere dense means that it's very far from containing a neighborhood. And of course we say that V is second category otherwise. So second category means it's impossible to write the set as a union of nowhere dense sets.
What's that saying? It says
Where the interior of the closure of the set E sub n for any n happens to be the empty set. So that's 2. Three. Recall that if we say that if V is second category, and En is a sequence of closed sets, such that V is the union then what? Then it's impossible that this union is a union of nowhere dense sets. Then at least one E sub n contains an interval. So here the discussion is just in R. So now let's try to state the Baire-Osgood theorem. Let Fn be a function from R to R, be continuous for each n. And suppose Fn goes to F pointwise. Where F is then also a function from R to R. Then the F is a first category set. In particular, F is continuous at a dense set of points in R. So before we prove this theorem, let's see what does it mean. So for D of f to be a first category set, it's a union of nowhere dense subsets. Now this is the set of discontinuities. If it's the union of nowhere dense, accountably many nowhere dense subsets, the complement, first of all, the complement we will show is going to be the intersection of dense open sets. And the complement is the places where the function is continuous. Okay? So something is stronger lurking in the background. So this is saying f is going to be continuous at a dense set of points. But that set of points where the function is continuous, does it have to be uncountable or not? In other words, maybe that dense set of points is just q. Maybe you have a limit function where the dense set of points is q, where it's continuous.
It must be uncountable by the Baire category theorem.
By the Baire category theorem, it has to be uncountable. Because again, what we will show is that we know that D of f is a union of closed sets, countably many closed sets. We will show that each of those closed sets is nowhere dense. The complement of that union is the intersection of open sets. That intersection has to be not only dense but uncountable. So in other words, what you can say if you know a little bit of Lebesgue measure and stuff like that, right? No, that's okay. But you can say that the function you are going to get is continuous almost everywhere. In other words, the set of all points where it's discontinuous, it's very small. It's countable, so it has measure 0. Basically, the probability of picking up a point at which the function is not continuous if you pick random is going to be 0. Okay? So the function will look pretty much very continuous. In other words, if you look at the graph of a pointwise function, if you zoom in at an arbitrary point without just some sort of knowledge or where to zoom in, just randomly, just move your lens on the graph and zoom in, you will zoom in at a continuous point. So let's prove. So we know that the set of all discontinuities of f can be written as the countable union of points at which the oscillation is not 0. So let's say 1 over n. So we wish to show that each is nowhere dense. Okay. To do that, we establish that for any epsilon bigger than 0, the set f, which is equal to x, such that the oscillation at f over x is bigger than or equal to, I did 4 epsilon, in Corollaries it does 5 epsilon. I think that works with 4 epsilon as well. It might modify slightly the argument. So 4 epsilon is nowhere dense. in R. So actually define sets En that are the intersections of all I, j bigger than or equal to n of x such that fi x minus fj x is less than or equal to epsilon. Then what can we say about those sets? First, the E sub n are closed. Because if I take this set x such that absolute value of fi x minus fjx is less than or equal to epsilon, I can define this as just the inverse image of some function phi ij of the interval minus infinity to epsilon included, where phi ij of x is just the absolute value fi x minus fjx, and this is a continuous function. So you understand why this is a closed set, right? So what we have is each is the preimage of some continuous function of the interval minus infinity to epsilon, and we take intersections of such sets. So intersections of closed sets are going to be closed. Two. On each En, we have that the magnitude of fi minus fj, it's the sup norm is less than or equal to epsilon for all I, j bigger than or equal to n. So in essence, we are imitating uniform convergence. Right? We are imitating uniform convergence, except that this is a fixed epsilon. It's a fixed epsilon. So I mean, the fact that I'm within this epsilon does not mean I can get closer, and E sub n is not an interval. Okay? Because limit as n goes to infinity of fnx is equal to f of x, we have that R is the union of those sets. So do you see that, that the union of En is R? Eventually, every point, right? Every point starting with some m is going to be satisfying this condition, because the Fn is Cauchy for every point x that you pick. So this is basically measuring. So En is picking all the x that start behaving, that starts becoming invisible under this epsilon. Right? So do I need to explain more, or you see it? To construct such a thing, it's just it's what's happening. It's a rather visual proof. So what you do is, if it's a uniformly Cauchy sequence, everything goes together very close to within epsilon, right? Everything goes together. But what happens if it's pointwise convergent? If it's pointwise convergent, if you look at the graph, you can look at different columns. So basically, imagine that over each x in the domain of this function, so over each x in R, there is a column. And that column represents all the images of this x under the different fn's. So f1 of x is going to be here, f2 of x is there, f3 is here, and you have a bunch of dots in each column. So each x is like a column. Okay? Now, pointwise convergence implies that if you look at this column, eventually, well, basically each column will look like it contains only finitely many elements. Why? Because most points, they are just clustering together. So you see a bunch of scattered points, but eventually you see that they're all clustered together. Now, in another column, they will all cluster together, but at another rate. So you might see more points. Like here, you look at the graph over the column x1, and you see 5 points. But you look over the graph at the column x7, and you see 20 points. What does it mean? The epsilon is your resolution, how good you can tell apart 2 points. Right? That means that the convergence over x7, or whatever the index I specified, is not as quick as the convergence for x1. Okay? So E sub n is measuring, is basically gathering those columns based on their speed of convergence. Does it make sense? So E sub n, if you understand my analogy of the columns, means that it gathers all the columns in which you see how many points. Here, let me draw it here. So what's happening is, when you think about such arguments, you can think graphically. So here is, let's say here is column x, here is column y, right? So here I draw okay, I did something like this. That's the column for x. Here is the column for y. So this x, if you see the intuition, it belongs to E sub what? 1, 2, 3, 4. Correct. This will belong to E sub 4. And this Y will belong to 1, 2, 3, 4, 5, 6, E sub 6. Okay? Does this make sense? So this epsilon that we specified, this particular epsilon, is your resolution, is how well you can tell that there are actually infinitely many points over x, potentially. There are infinitely many points over y, potentially. But you will not see this as such. If you have convergent function, if you have pointwise convergent functions, you will not see it as such. Make sense? Yes?
Columns don't necessarily have to be in order.
No, there is no order. I mean, how would I impose if there are uncountably many columns, right? But graphically, you can think of this as basically what the ENs are doing are just they're gathering all the x's that have somewhat of the same speed of convergence. Somewhat, right? So this is just roughly what's happening. So the intersection is just a set way of describing that. But what you're doing is, whenever the 2 points, whenever fi and fj they are less than epsilon, they look to you like they are one and the same point. You see? So that means that starting with let's say apparently it depends on how I draw it. So let's say this is first, this is second, this is third, this is fourth, this is maybe this is first, this is second, this is third, this is fourth, this is fifth, and this is sixth. So start basically they are all the sixth. This point is where if you zoom in, you actually see infinitely many points. If you zoom in, you might actually see infinitely many points. But under the resolution epsilon, they all appear as 1 point. Okay, that's the intuition here. So over En, it is kind of like uniform convergence, right? I'm gathering the columns over which the convergence is somewhat like uniform. For that, but it's not, it's not really, it's a little weaker than uniform convergence. I'm gathering them where they all disappear to 1 point after the nth iterate. Sorry. Okay. So do you see that if I gather all the columns, all the x, so I will gather R, in fact. Because we have a pointwise convergence for each column that I pick. It eventually starts looking like a finite number. The finite number that it starts looking like is it's going to be the set E sub n that contains it. So R is the union of those sets. I hope it makes some sense. Okay. So let me ask you a question about those sets En. Are those lower dense sets? Are they lower dense?
Well, one has to contain the interval.
Yes, absolutely. One has to contain an interval. Why? Because it's a countable union and we have written R. Right? If we take a countable union of lower dense closed sets, I said they're closed, right? If I take a countable union of lower dense closed sets, the complement is going to be an intersection of dense open sets, which will, by Baire theorem, will prevent us from containing R, right? The complement will have had to contain uncountably many points that are dense in R. So this fact tells us that one of the En at least has to contain an interval. So what we do is, first of all, we actually let I be any closed interval we want to show that I is not contained in the set F where if you recall, f is oscillations that are bigger than 4 epsilon. If I want to show that this set is nowhere dense, it contains no interval. It's already closed. So what we can do is I is the union of En intersect I, since I is second category. Remember, every interval is second category. Not all the En intersection I are nowhere dense. In particular, there is an interval J which is in En intersect I. Or something. So now I'm going to actually draw this interval. So this is the interval J, and J is contained in En intersect I. And if I pick, I want to show that this interval J is totally disjoint from F. So I will show that this J is completely disjoint from F. How do I do that? Well, pick any point X. I know it's hard to follow me, but what do I want to show about X? So here is the set F. I want to show this point X that I picked is not in F. What does it mean? It means that the oscillation at X is not as bad as 4 epsilon. Right? So the bigger the oscillation, the less continuous it looks locally at this X. Right? So I'm going to show that at this X, the oscillation cannot possibly be too bad. So what I do is I take this X, and how do I measure oscillation? I just pick any 2 points around X and I push them close to X, and I measure the oscillation in that region. So I pick some Y and I pick some Z. And then I want to see what's going to be an estimation of the oscillation at X. So that estimation is F of Y minus F of Z. This is going to be less than or equal to F of Y minus Fn of Y plus Fn of Y minus Fn of Z plus Fn of Z minus F of Z. Now, the fact that this interval belongs to E sub n means what? Means that F of Y minus Fn of Y, that this thing, it's like almost uniform convergence. This thing is smaller than epsilon. Right? So that's smaller than, first guy is smaller than epsilon, plus the middle guy I won't touch for a moment, so I'll keep it as fn y minus fn z. And the last guy is also smaller than epsilon. Everything in this interval, basically what I have done using this, it's a very difficult, clever trick, but what I have done is I've actually found out that if I look at all those columns, I will find an interval of columns over which the functions all have the same number of elements. That's graphically what's happening. So imagine that you're watching those myriads of columns, and somewhere in this over R, you observe that over some segment of space, over some interval, all the columns look like they have, let's say, 6 elements. Okay? In particular, it means that starting with the integer 6, the differences between the various fi's and fj's, they vanish. So then what you do is that, what is this thing going to do, the middle guy? The middle guy is going to be also less than epsilon. If y is close to z by continuity of fn. So remember that the sequence of functions is continuous. So what I have is 3 epsilon, and 3 epsilon is less than or equal to 4 epsilon. In fact, let's say strictly less than 4 epsilon. So the implication is that the point x does not belong to f. And the implication of that is that j is entirely in f complement. And the implication of that is that I, which contains j as a subinterval, cannot be in f, because part of it is not in f. So that's done. So at first glance, a bit of a difficult theorem. So let's look at the corollary. Let f be a function from R to R. Then the set of all discontinuities of f is a first category set in R, if and only if f is continuous at a dense set of points. So it's not even a corollary of the theorem, that's almost obvious. I mean, we can say that the set of all discontinuities is an F sigma set, which is nowhere dense if and only if its complement is dense. So example A, if you look at psi of q, it cannot be written as a pointwise limit. Now, why can it be written as a pointwise limit? What's wrong with xq?
Everywhere.
It's everywhere discontinuous. Wonderful. So you can say that R is equal to the discontinuity set of x sub q, the characteristic function there, which is not first category. You understand that the only possibility for a function to be a pointwise limit of continuous functions is that if the set of discontinuities is first category. That's what Baire-Osgood theorem is telling us. In other words, pointwise limits do not produce too many discontinuities. Anybody knows about condition for integrability? A function doesn't have to be continuous to be integrable, correct? What must be true for the function to be integrable? Anybody knows?
The discontinuities will measure 0.
The discontinuities must have measure 0. So here is possibly, I'm not sure if others see this. If I have a function that is the limit of a pointwise limit of continuous functions, is it integrable? Yes. Hopefully we're gonna cover Riemann integrability, so you'll see more about it. But the answer is yes, right? So every function that is a pointwise limit of continuous functions is integrable, according to Baire-Osgood. Riemann integrable. Okay. B. Here's another thing. If f is everywhere differentiable, if f is everywhere differentiable, then f prime has to be, I'll call it frequently continuous. So the derivative is frequently continuous. Because f prime is equal to, let's say, f prime of x is the limit as n goes to infinity of n times f of x plus 1 over n minus f of x. Correct? If you prefer, you can write this n like this, 1 over n. So what's derivative? It means f of x plus a perturbation minus f of x divided by the perturbation, by that's something that vanishes to 0. So this is a sequence of continuous functions, right? For each n, this is a continuous function. So by Baire-Osgood, it means that if I find that my function is differentiable, then it's almost everywhere continuous. The derivative is almost everywhere continuous. I'm afraid to start something I might not finish. So even the words worry me a little bit. So we have seen examples, like a formula example, that a function is nowhere differentiable. But you can show the existence of nowhere differentiable functions that are continuous in the following way. So if you just gather all the functions that are differentiable at least at one point, that collection of functions is a first category set. Since the space of continuous functions is complete, that means that the complement is an intersection of open dense sets, therefore dense, right? So there are lots of functions that are nowhere differentiable. So what we're going to do, we're going to consider the right-hand derivatives. We're going to see each E sub n is going to contain all functions that have a right-hand derivative somewhere. And actually, there is a restriction on the right-hand derivative. That's because the way it's written, h is allowed to not be infinitesimal. H is allowed to be a number. So we restrict x to be from 0 to 1 minus 1 over n, so that h does not exceed 1, essentially. So if f belongs to C01 has a right-hand derivative, of size at most n, in the interval from 0 to 1 minus 1 over n, then this function belongs to E sub n. So the set contains all functions with bounded right-hand derivative. In the interval close 0, open 1. It contains possibly more than that. So then we observe the following. Each E sub n is closed You still follow me, guys, right? That worries me quite significantly. This is a very hard theorem, and there is actually, I want to reveal, there is one part in this theorem that I am bothered with, actually this part. Right, because this part is not equal to the right-hand derivative being bounded at n. It's stronger. And because it's stronger, that bothers me, right? But let's pretend that right now it's okay, since we have only, 8 minutes. You see, the idea of how you construct such things is you categorize the types of derivatives that you have based on their size, right? So the magnitude of each derivative, if it exists, is less than, in absolute value, less than some number n, right? So this proof only looks at the right-hand derivative. So if a function is differentiable, in particular, it has to have a right derivative, correct? So it basically tries to gather all the functions that have a right derivative and then show that if you look at this gathering, it can be written as a countable union of no-ordered sets. And that tells you that we haven't gathered too many functions. There are many, many, many other functions that are not included in this collection. So I hope I am not losing you. Suppose, so first I want to show this is closed. Suppose Fk is a sequence in E. And so suppose I picked a sequence. So in the sequence, what we have is that in the sequence, those functions have a point at which the derivative, at least one point at which the derivative is bounded by n. The right-hand derivative is bounded by n. So we want to show that f also has a point at which the derivative, the right-hand derivative, is bounded by n, and that makes f a member of E sub n. So there is a corresponding sequence such that so because this interval 0, 1 is compact without loss of generality, we can say that xk converges to x. If it's not converges to some x, then take a subsequence. So now I'm going to try to estimate the right-hand derivative at the point x for the convergent function. So we have absolute value of f of x plus h minus f of x. And I break it into f of x plus h minus f of xk plus h plus f of xk plus h minus fk xk plus h plus fk xk plus h minus fk x sub k plus fk xk minus f of x. And this thing is less than or equal to absolute value f of x plus h minus f xk plus h plus this middle guy by uniform convergence. You see they have the same element, so that's plus f minus fk subnorm plus Now this guy is bounded by n times h. And the last guy I can leave as fk xk minus f of x. And the entire thing if I push k to infinity, the entire thing will vanish. So this goes to 0. This goes to 0, so the entire thing, and this will go to 0. So the entire thing is just approaching NH. So we have shown that f of x plus h minus f of x is bounded by n times h, which implies f is in E sub n. So just one small part left. So each En is nowhere dense. So what you do is if G belongs to E sub n, I'm going to show that there is no open ball that contains G. So that can be done graphically. So let's say G is some function like this, and therefore this is a picture of the open ball. I want to show that next to G, within this bound, there is a function all of whose derivatives, if they exist, are bigger than n. So G, if it has some right-hand derivative that is bounded above by n. So I can construct very easily a function whose derivatives, just you build them out of line segments. So take a line segment, make it very steep so that its slope is bigger than n. This is negative slope, smaller than minus n, and continue doing like this. So a zigzag function made out of line segments. In places it's not differentiable, but wherever it's differentiable, let's call this function f. So clearly f is not in E sub n. And the proof is complete. This is the easier part. Okay. So each function that has at least one right-hand derivative bounded by n can be approximated in the sup norm by a function that all of whose derivatives, whenever they are defined in absolute value, are bigger than n. So what you do is build that function out of line segments. Just make because line segments, it's very easy to control them. Just make them steep. If you make them steep enough, the slope is bigger than n. So that's the easy part. All right. Now again, one thing that I don't like about this thing, I wonder if it matters, is the fact that we allow it for all h. That it's not written as a derivative, but for all h. Usually, when you just look at the derivative, you take a limit as h goes to 0. So I wonder if this is significant. All right. I hope you wonder if this is significant too. Good night.